This is a very short section called solving trigonometric equations with multiple angles, and it's the multiple angles here part that's important here. An example would be to solve something like solve the sine of 3 theta equals a half. And when I say multiple angles, I mean this. One of the examples given in your textbook is solve the cosine of 2 theta, or 2, do they use theta? No, they use x. The cosine of 2x. And I want to avoid that example primarily because we have a double angle formula for that. So that might be confusing. The double angle formula for sine of 2 theta is 2 sine theta cosine theta. And then if I divide both sides by 2, I get sine theta cosine theta equals 1/4. And there's really nothing I can do with that. So it's tempting to go that route because you have a double angle, but there are times when you have, well, first of all, there are times when that's not going to help, as in this time. And there are also times when the angle you're given is not a double angle, but a triple or a quadruple angle. So I'm going to start with that example. Let's start with sine of 3x. Now here I don't even have a formula for the sine of a triple angle, so there are ways I could go about rewriting this, but I'm not going to get into that because the point really here is that I don't necessarily need to, because I know, for example, what the sine of an angle is, that when the sine of an angle is a half, that 1/2 is very messy, it's making me upset. I want to write it a little bit more neatly. That if this was sine of t equals a half, well, I would know what the solution to that was, right? T there has to be pi over 6. And I can get that from a table or from a unit circle. If I'm looking for solutions in quadrant 1, I'm finished. If I'm looking for solutions between 0 and 2 pi, then I need also, let's see, it would be 5 pi over 6. That's the one in quadrant 2. There are no solutions in quadrants 3 or 4. If I wanted all solutions, I would have to say plus 2 pi k. The point is, though, that I know how to solve problems like this, depending on whether I want one solution, all solutions between 0 and 2 pi, or all solutions everywhere. Depends on how much information you have to give here. But I know how to find those primary solutions, right? And the same thing is going to occur, or the same thing needs to happen here. In fact, what I can do is say, let 3x equal t, or some other variable of your choosing. Once I've done that, and I have my solutions, I have t equals pi over 6, and t equals 5 pi over 6. Then I can just back substitute or resubstitute 3x equals pi over 6, and 3x equals 5 pi over 6. Now to solve for x, all I have to do is divide by 3. Dividing by 3 is the same as multiplying by 1/3, so however you need to do that to make you happy is fine with me. X equals, this is going to be pi over 18. And this one is going to be x equals 5 pi over 18. And if I only need, I'm kind of tempted to, I'll use a highlighter. If I only need the solutions between 0 and 2 pi, then I'm done, right? I have found all of the angles that satisfy this equation by substituting t for 3x, all of the solutions between 0 and pi that solve that equation, and then I've back substituted and solved for x. I have found all my solutions. This is not a hard thing to do. What gets most students is what happens when you have to add the plus 2 pi k. So we're going to talk about that next. I'm going to erase some of the screen here and move some things around. I'm not actually sure how long it's going to tell. That's not too bad. Those are my two final solutions. If I have, if I need to find all solutions, then there are two places where you might consider adding your plus 2 pi k, but there's only one right place to do it. And here's why. If I solve this equation and I just assume that these are my solutions, and I continue and then add plus 2 pi k here. I'm going to take pi over 18 as one of my solutions, and I'm going to go all the way around 2 pi, all the way around the unit circle. Pi over 18, where would that be? It's really small. Pi over 6 is about there. Pi over 18 is a third of that. So we're going to call this pi over 18. And if this is my first principal solution and I say plus 2 pi k, then I have to go all the way around here to get to a coterminal solution. But it turns out that there are intermediate solutions. And here's how we can tell. If I know that the solution to this equation is pi over 6 and 5 pi over 6, and I add my plus 2 pi k here, then when I resubstitute, get my pointer here, when I resubstitute 3x for t and I divide both sides by 3, I'll be dividing this by 3 as well. So I'm taking the 2 pi, the full circle, and dividing it into thirds. So there are actually 3 solutions where it looks like there's only one. So let me erase a little bit more, and I'll just go back. In fact, I'm going to go back. I'm going to erase this line here, and I'm going to go back to, well, let's just get rid of the whole thing. I'm at the point where I'm ready to solve. I've solved this solution, or solved this equation for its 2 solutions within the 0 to 2 pi range, but I've added plus 2 pi k to indicate that there are an infinite number of additional solutions. Now I'm going to back substitute, and notice that I added my plus 2 pi k before I back substituted. 3x equals pi over 6 plus 2 pi k. 3x equals 5 pi over 6 plus 2 pi k. When you solve an equation, or when you isolate the variable, you need to divide both sides by 3. And that's the equivalent of saying x equals pi over 6 divided by 3 plus 2 pi k divided by 3. We got pi over 18 for this part, but then I also have plus 2/3 pi k, or you could write that as 2 pi over 3 times k. Similarly, here, this equation here, this version here, when I divide both sides by 3, I'm going to draw a dotted line here to separate my two answers. I get x equals 5 pi over 6 divided by 3. That's going to give me 5 pi over 18, plus 2 pi k divided by 3. And actually, if you want to, you can certainly leave this part of the answer in this form here, or you can rewrite it like this. So this answer is going to be 5 pi over 18 plus 2 pi k all over 3. 2 pi k all over 3. You can write that as 2 pi k all over 3, 2/3 pi k, or 2 pi over 3 times k. Those are equivalent. So you can use whichever of those forms that you prefer. Let me point out, though, that if I start at pi over 18, for example, which is this very small angle here, and I add 2/3 of a pi, that's pi. 2/3 of pi is about here. So it's this angle plus 2/3 pi. That's if k is 1. If k is 2, I'm going to add another 2/3 of pi. So it puts me about here. If k is 3, I get 3/3 pi k, which puts me back here. If I had just said x equals pi over 18 plus 2 pi k, then I would have this solution and not another one related to this until I got all the way around. So if you wait until you get here to say plus 2 pi k, it's too late. You've lost, in this case, 2/3 of your solutions. So it's important to add your plus 2 pi k up here when you solve for t, the variable you substituted in for 3x. Now these problems, when you see a problem like this might be a 3x or a 5 theta, or it could be a 2t, for example. It could look like a double angle formula type of problem. It just sort of depends. If you try the double angle and you can't get anywhere, you might try substituting in for 2t and solving it this way instead. But other than that, this is pretty much the approach you want to take for these kinds of problems. Replace the multiple angle with some other variable. If you have an x here, you could use a t or a theta here. If you have a theta here, you could use an x or a t, or an alpha or a k, whatever makes you happy. Actually, k might not be the best choice because we're using a k here, so the context is important. Anyway, find some other letter to use, replace all of the argument of sine or cosine or tangent with that other letter, solve this simpler problem, add 2 pi k to each solution before back substituting. But once you back substitute, finding your answers should be pretty straightforward. And that's it for this video. In our last video of this section, we're going to learn how to solve right triangle problems.